Hey audience, let's read some datasheets. In a couple videos now, I've talked about problems that I've had driving clock signals from a CMOS output into a TTL input. And I originally just said, oh, logic level's incompatible, and then tried to forget about it, but it kept bothering me. The problem is that logic levels actually are compatible from CMOS to TTL. It's when you're driving a CMOS input from a TTL output that the levels are technically incompatible, but I haven't even had any problems with that. And also, the clock seemed to work when I was only asserting the J or K inputs of the flip-flop, and it was only when I was asserting both J and K to make it toggle where the clock didn't work. Even when driving it from TTL outputs from switches, it would sometimes toggle and sometimes not. So it seemed like more of a timing issue. Maybe if the rise time of the clock was too long, then it was toggling twice before the clock stabilized. And I got a hint when I took a closer look at the chip. It's a 74F109. And you know what the F stands for?
Fist.
So I looked up the datasheet for the F-series version, and sure enough, right here there's a line. Although the clock input is level sensitive, the positive transition of the clock pulse between the 0.8 volt and 2 volt levels should be equal to or less than the clock to output delay time for reliable operation. And the clock to output propagation delay is in the single digit nanoseconds. And the 74HC04's output rise time, that's the CMOS chip that was having trouble driving a clock to it, is in the double digit nanoseconds. So mystery solved. But later when I went to look up the datasheet again to make a video about it, that line wasn't there anymore. Instead, there was a line that said, clock triggering occurs at a voltage level and is not directly related to the rise time of the clock pulse. Turns out there were multiple companies that made these chips, and I'd just found a different version of the datasheet this time. So I found the previous one that I looked at, but when reading the description more carefully, above the part about how rise time matters is the line, clock triggering occurs at a voltage level and is not directly related to the rise time of the clock pulse. Literally the same text as from the other brand's datasheet, saying that the rise time doesn't matter. Alright, so I tracked down every version of the 74F109 datasheet that I could find from different brands, along with the 74LS109, because I had a hunch that this was a copy-paste error from an earlier datasheet. Then I made a map of what I found based on the release dates, the update dates, and some Google searching of the companies. The earliest datasheets seem to be from TI. Their LS datasheet was released in 83, and their F datasheet was released in 87. They both have exactly the same descriptions, because of course they do, like there's no reason to update that. And both of them claim that the rise time of the clock pulse doesn't matter. Then it looks like Fairchild made clones of these chips, releasing the LS datasheet in 1986. And then they released their F version in 1988. The description in the LS version of their datasheet looks suspiciously similar to the wording from TI's version, and I'm guessing TI's lawyers thought so too, since the F version of Fairchild's datasheet has a completely different description from the LS version of it. But in any case, both of them say that the rise time of the clock doesn't matter. National Semiconductor also has a version of the 74F109, and they released their datasheet in 1994, and it has the exact same description as Fairchild's datasheet verbatim. So how did they get away with that? Well, National bought Fairchild in 1987. That was actually before the first release date on Fairchild's F109 datasheet. So why is there even a Fairchild branded version of the F109? Well, it turns out National actually spun off Fairchild again in 1997, and then Fairchild became its own company again. I'm assuming that's why the Fairchild datasheets have update dates that are more than a decade after their release date. Those updates were probably just changing the branding back to Fairchild, or maybe changing the branding to Fairchild in the case of the 74F109. On Semiconductor also has an LS series datasheet with wording that is very similar to Fairchild's F series datasheet, but actually not at all similar to Fairchild's LS version of the datasheet. On's datasheet is dated as December of 99, a month after the most recent update of Fairchild's F series datasheet in November of 99. On Semiconductor did buy Fairchild in 2016, so maybe they just slapped their branding onto Fairchild's most recent datasheet without changing the date, or maybe they backdated it. The fact that they copied the wording from the F version of the datasheet and changed it to LS instead of just copying the LS datasheet, I think it's just more evidence that there was some sort of legal dispute over the wording between TI and Fairchild. But there are still no mentions of the clock rise time being important, which brings us to the third and final player, Philips, which eventually rebranded as NXP, but otherwise seems to be independent from all of these other companies. They released an F109 datasheet in 1990. The wording in their description appears to be mostly unique, but it does lift one sentence verbatim from TI's version of the datasheet, which just happens to be the sentence that tells you that the rise time of the clock pulse doesn't matter. And then the sentence about the rise time actually being significant is just bolted on at the end of their description. This is pure speculation, but I'm guessing what happened was both TI and Fairchild/National didn't notice that rise time became significant in the F-series version of the chip. I'm guessing Philips noticed when their tests failed and then found that TI's chips in their testers had the same behavior, so they just slapped an extra disclaimer in the datasheet and moved on. They were already last to market with these, and it probably took time to figure out what was going on, so in their rush, they just left the original sentence in by accident. The schematic diagram in the Philips datasheet also seems to imply that this was a bit of a rush job. For instance, if we follow this gate's input, we can trace it back to this other gate's output. But this gate's input gets traced back to another input. They just forgot to put a dot here. It's not a big deal, I just thought it was kind of funny. So the takeaway here is that for some synchronous logic, they need to be compatible not just in terms of voltage levels, but also in terms of timing as well. But does any of this really matter? No. None of these companies are going to care enough to update their datasheets decades later to fix a problem that no one will run into for chips that no one is even using. The only even remotely recent devices I've seen using any 7400 series logic are mostly using bus drivers, with the occasional inverters or gates for glue logic, with more recent designs using CPLDs or FPGAs for glue logic. I don't think I've even seen synchronous logic 7400 series chips used in real designs. I'm sure they're out there, but I'm also sure those designs are old. But then again, TI is still selling these, so who knows. Also, the fact that the K input is inverted just so that it's easy to turn into a D-type flip-flop tells me that this chip is meant more as a Swiss Army knife flip-flop when prototyping a logical design on a breadboard. Need a flip-flop? What kind? Doesn't matter. You can use a 109. And even in a prototyping or educational context, you'll probably be using the same logic family everywhere, and this problem won't show up if you're only using 74F series chips. Really, the only time this problem ever shows up is when some hobbyist buys a grab bag of random TTL chips. So, me. I'm probably the only person this could or ever will happen to. Or maybe it could happen to you too. And now when this inevitably happens to me again, I'll have an idea of what's going on. I'll see you then.